Well, hello, ladies and gentlemen. Topics for today, we're going to review the concept of work and how to calculate boundary work, and this is from last lecture. And then we're going to move on to the other path function. Remember, we started off this chapter looking at path functions. There are point functions, which are a function of the state of the system and not how the system got there. There are path functions, which are a function of how the system moves from one state to another. One of the path functions that we introduced last time was work. And in particular, we derived the expression for boundary work. And we did an example where we had to calculate the boundary work of a system. And today we're going to introduce a second path function, which is heat, or heat transfer Q. And we're going to go over the details of that. So topics today, we're going to look at heat transfer, how heat transfer is defined, what are the bases of heat transfer, the forms of heat transfer, how are they expressed? And then we're going to introduce quantities called specific heats. Specific heats tell us how a system's temperature changes. A system's temperature changes as we add heat. And as you might guess, the temperature change of a system depends on the path taken when we add the heat, because Q is a path function. So we're going to talk about specific heats. We're going to round off the lecture talking about specific heats, how they're defined, what they are a function of, and then we'll do an example involving specific heats, their application. All right? So let's review a little bit from last time. So we have boundary work. Boundary work, bound, and this is from, let's say, state 1 to state 2. So we have a system which moves, and I have a PV diagram, a pressure and volume diagram for the system. A system which moves from state 1 to state 2 along the path that you see here. The area underneath this curve represents the boundary work over the process 1 to 2. So W bound 1 to 2, that's the area underneath the PV curve. Mathematically, boundary work is defined as the integral of PdV as we go from volume 1 to volume 2 along the path 1 to 2, okay? So that's how boundary work is calculated. By the way, so the system is starting off with a certain volume, and let's say it's expanding. So our system here, I guess I'll stay down here. So our system is moving from state 1, so I have a pressure, I have a volume V1, I have a bunch of initial conditions here, and it goes to state 2. Let's say it's expanded a little bit from state 1 to state 2. So now I have a PV pressure and volume at state 2. So it's expanded. It's expanded, the piston has moved upwards. So clearly the system, and I mean the system is the gas inside. So here's our system control volume, so the gas inside. So clearly the system has expanded, so it's done work because it's expanded against the weight applied by the piston, and there's a pressure inside. Because it's expanded, it's done work. So this quantity here, this integral here, is work done by the system. When the system does work, which is the integral of PdV, is positive. If you do work on the system, so if I'm squeezing it down instead of letting it expand, I'm doing work on the system, then the volume change is negative, and this integral will be negative. So if that integral is positive, work is being done on the system, by the system, work done by the system. If W is equal to PDV is positive, and if that integral is negative, that means you're doing work on the system, on the system. So work is positive when you're doing it, when the system is doing work, and it's negative when you're doing work on the system. So that's boundary work from last time. Let me show you some additional forms of work. Let me show you some additional forms of work. There's not just boundary work, there's other forms of work. So other forms of work. Two kinds. Let's go over them one at a time. Actually, there are three kinds. We'll encounter the third kind a little bit later. There is shaft work. Shaft work. W shaft. So let's say we have a system and we have inside the system a little propeller. Okay? So there's a little propeller in here. Little propeller, and this propeller is spinning around. Okay? It's a propeller on a shaft and it's spinning around. Now, this shaft attached to the propeller is applied, this has a certain speed, so we have a certain angular velocity. Omega is angular speed, and that is in radians per second. So it's angular speed in radians per second. And there's also a torque applied at the shaft. There's tau, which is torque. Okay? There's tau, so we're applying a twisting force to the shaft. There's some resistance being encountered to spinning the shaft, and it spins at a certain speed. And the shaft work, or the rate in which shaft work is done, W dot shaft, which is a little bit of shaft work over a little bit of time. Little bit of shaft work, see the delta here? Delta shaft work over time is equal to the torque times the angular velocity, tau times omega. You multiply these two things together and you get power. You get power. So the shaft power, or shaft work per unit time, done by the system, is equal to the torque times the angular velocity. And you can see that, so torque times angular velocity, let's look at the units here. So torque, let's say, has a unit of, let's just do it in general. It has a length, L, times a force, F. So that gives me a torque, a length times a force. And then I have omega, which is unitless. It's radians per second, so that's unitless. And then I have time, t. So a length times a force divided by t, that has units of a length divided by time times a force. So this is a velocity. Velocity times a force. Velocity times a force. So torque times angular velocity gives me velocity times a force, which is power. Power. Work per unit time. work per unit time. So shaft power, W dot, is equal to the torque times the angular velocity, okay? So that is shaft power. Shaft power. Now there's another kind of work, or power if you like. And remember here, we're talking about a mechanical transfer of energy. That's how we defined work in general, as a mechanical transfer of energy. There's also electric power. Electric power or work. If you like, work per unit time. Work per unit time. Electric power. So we have a system. So here's our system. And instead of having a shaft in there, instead of having a shaft, we have some wires. Okay, we have some wires here. Here we have a resistor, or I guess that looks more like an inductor. Okay, so we have a resistor here, R, and we have some current flowing through the wire. So we have some current flowing through the wire, through this resistor. So, and if you like, there is a voltage difference as a result of that across this resistor. So there is a delta voltage. It's a delta voltage across the wire or the resistor or the device that is dissipating energy caused due to the current flowing through the resistance. The electric power, W dot electric, is equal to the current times the voltage. So I times delta V. And remember, the definition here is the same as in the shaft power case. W dot electric, so I'm going to move this over. W dot electric is the little bit of electric work over a small period of time, and that is W dot electric, okay? So we've encountered now three forms of work, or power if you like. There's shaft work, there's boundary work, which has to do with the change in volume of the system. We have shaft work, which has to do with putting a little propeller or impeller into the system and spinning it. So we're adding energy to the system or receiving energy from the system by spinning the shaft. And the shaft power is equal to the torque times the angular velocity. So a little bit of work over a small amount of time, or a rate in which work is done. And then we have electric power. The rate at which electric work is done, W dot electric. W dot electric is I times delta V, the current times the volt drop across the resistor, okay? So three forms of work. Three forms of work. So that's work, ladies and gentlemen. That's work. We've done an example involving boundary work. If you go through and you look at your notes, you'll find that there's an example on shaft power. There's a problem that involves, I think it's boundary work and shaft power or electric power together. Or maybe that's later on. So just look through your notes. Talks a little bit more about shaft and electric power, okay? All right, let's move on to our next topic, which is our second path function called heat. So let's go over heat. Actually, let's take a short break here.